Good morning. Today we're going to talk about section 7.3, estimating a population mean. Well, let's take a look back at 7.2 before we go on to 7.3. In 7.2, we learned using TI-83 calculator capabilities to estimate a population proportion P with some characteristic of interest. Well, you recall what we did. If we're considering a huge population and we're considering a population proportion with some characteristic of interest, typically we'll never really know for sure. Populations are too big to study element by element, so we can't get an exact value from this. But what we can do is from a sample, grab a sample proportion with some characteristic of interest. We call that p hat, and we computed a confidence interval estimate based on p hat. Now what the calculator did using the one-prop zint command, calculated a margin of error and gave us an interval of values. Now the idea was, well, does p land within these bounds? Hopefully so. We could say with a certain level of confidence we can claim it so. And to calculate that confidence interval, we used the calculator used this formula, which we never really calculated by hand directly. But the reason I write it down, our margin of error, cap E, is based on a z-score, hence the name for this command, one prop z interval. One prop because we're looking for a estimation of a population proportion, a z because our margin of error is based on a z-score, and int because we're constructing a confidence interval. Alright, recall our final answers for this section look something like this. A double-sided inequality indicating high and low bounds for our estimate of little p. Alright, so that's what we did in 7.2. And in 7.3, I think we'll find the structure is largely the same here, but we're going to be estimating a different quantity. In 7.3, we're going to be estimating not population proportions, but estimating population means. Alright, again in wide strokes, we're considering a large population with perhaps billions of elements in it. Our population mean, you may recall the symbol for population mean is your Greek lowercase letter mu. And typically, we never really know what mu is. No way to find out exactly because we've got millions, maybe billions of elements in this huge population. Well, what's the next best thing? Well, the next best thing is to take a sample, a more manageable sample, and from a sample we can compute a sample mean. Now, we call the notation for sample mean as x bar. Now, perhaps x bar, our sample mean, is a good approximation for the population mean. Maybe it's not. Well, in any case, x bar, our sample mean, is what we call a point estimate of mu, our population mean. And like we said, maybe it's a good estimate. Hopefully, if our sample is representative of the population, it's a good estimate. Well, again, we never know for sure. Well, the idea here is maybe there's a better way. Instead of picking a number and calculating that and approximating mu with that number, that single number, our goal is this: to create a confidence interval estimate for mu. Again, our goal is to come up with a interval, a bounded region of real values, which hopefully will contain mu, at least with some probability or some known level of confidence. All right? Our book talks about part 1, and we're going to restrict our studies in this section to part 1. We're going to estimate mu, not p in this section, it's mu in this section, when sigma is not known. Alright, we're going to assume the population standard deviation is unknown. Remember, sigma, our lowercase Greek letter sigma, represents the population SD. Okay? So we make the assumption that sigma is not known, and we make some underlying assumptions here also. Our population is approximately normal, or your sample size is greater than 30. All right, one of these two statements have to be true to use the formulas developed in this section. The formulas developed in this section do make that assumption. All right? Our goal is very similar to the one in section 7.2. We're going to create an interval estimate for mu here, not p, mu in this section. And we're going to do it based on sample data, in particular our sample mean, right? Our sample mean will center our confidence interval estimate, and again our calculator will compute a margin of error, and again the calculator does that upstream, which represents an offset from which we will successfully add and subtract from x bar to create a range of values. Alright, well, our formula for E in this section, again, the book doesn't derive it. It may be beyond the scope of this course, really. Right, it should look somewhat familiar to the formula for E, which we saw in section 7.2. It's T sub alpha over 2 times S over the square root of N. Now, T is a t-score, very similar to a z-score. T-score is based on a t-distribution, and we'll talk more about that later, perhaps in the face-to-face class. S is our sample SD, our sample standard deviation, and of course N is the sample size. So we've got a square root of N in that denominator. Now don't panic. Again, the calculator computes this E value, but I do want to show you that that margin of error is based on a t-score, not a z-score. Right, we're going to be using a new command on our calculator, which I'll show you when I get a new screen here. Alright. Alright, we're going to use the TI-83 or 84 command called t-interval. We're going to be creating an interval estimate for mu. Again, it's based on a t-distribution, hence the name t-interval. Alright, let's jump right in and do a homework problem. Number 9. This is number 9 on page 357, and I believe this one is in your homework list. You may want to pause and turn there and get familiar with the problem. I'll read it here. Alright, number 9 talks about earthquake depths. It says data set 16 in Appendix B lists the depths of a sample of 50 earthquakes. These 50 depths have a mean of 9.8 kilometers and a standard deviation of 5.013 kilometers. Construct a 98% confidence interval estimate of the mean of all such earthquake depths. Alright, so again, we've got a huge population of all earthquakes of all time, and the population mean for the depths of the centers of all earthquakes we will consider as mu. an unknown and unknowable value. Alright, what we're going to do is this. Let me write down the given information. We had a sample of size 50. Right? The sample mean depth of all these earthquakes is 9.808 in kilometers. Our standard deviation from this sample is 5.013 in kilometers. All right, we're going to use this sample data to create what the book says a 98% confidence interval estimate for mu. Okay? All right, our level of confidence, referred to formally as 1 minus alpha, is 0.98. So we want to create an interval such that we will be 98% certain, or have a 98% probability of actually containing mu. And we're going to use, again, this t-interval command on our calculator. Again, t because we're using a t-score, at least internally in the calculator, and interval because we are constructing a confidence interval. Alright, you'll find it in the stat test menu on your calculator. You may want to get your calculator out, hit stat button, then from that menu highlight and enter on tests, and then scroll down until you see the t-interval command. Alright, we'll run you through it here. You'll see an input screen that looks something like this. You will have an input option for this command. You can pick either a raw data option or a summary statistics option. Now if I look at my sample data, we were not given raw data, we were given summary statistics for this data. So I'm going to want to enter this mode, highlight and select the stats input mode, and you'll see then the calculator prompts you for some things. It prompts you for these summary statistics. Alright, so my sample mean, well, we know that's 9.808, so go ahead and enter that in. SX, cap SX, remember that is our TI jargon for sample standard deviation, 5.013. Our sample size was of course 50, so I'll enter that in. And of course, once I enter all this necessary data in, I'll highlight and enter calculate, and I get the following result screen from this command. Alright, this is the confidence interval right here in parentheses notation. Alright, the calculator also lists your sample mean, your sample standard deviation, and your sample size as you entered. Gives you a way to check, make sure you entered in the right data. Alright, so I'm going to claim that this is my 98% confidence interval estimate for mu. I've got a range of values indicated by this double-sided inequality. Now notice in 7.3 we had a P in between these inequality symbols. Here in this section we're not estimating P, we're estimating mu, a population mean. And I can label this very easily. This is my 98% confidence interval estimate for mu. All right. Well, mu is the population mean depth for all earthquakes of all time. Right? In kilometers, right? So this is my confidence interval estimate for mu. And I can add an interpretive statement here. I could say, well, informally, I could say 98%. We could be 98% sure that mu is between these limits. A little more formally, I could say this: 98% of similarly constructed interval estimates will actually contain mu, the population mean. We'll never know for sure, but here we could be 98% sure. Alright? So the emotions of it are largely similar to what we did in 7.2, but again, we're estimating a different quantity here, namely a population mean. Let's look at number 10 on page 357. I'll read it here. Alright, number 10, they talk about mercury levels in sushi. Alright, listed below are the amounts of mercury in parts per million found in tuna sushi sampled at different stores in New York City. The study was sponsored by etc. etc. Alright, the sample mean is 0.719 and the standard deviation is 0.366 in parts per million. Construct a 90% confidence interval estimate of the mean amount of mercury in the population. Now notice, in this problem, they give us the summary statistics, but they also give us the raw data. I'm going to use the raw data and enter this raw data in the raw data mode in my t-interval command. Let me show you how to do that. Let me get this data down. Alright, so here's our sample of 1, 2, 3, 4, 5, 6, 7 restaurants with their sushi fish mercury levels: 0.56, 0.75, 0.1, 0.95, 1.25, 0.54, and 0.88. Alright, let's say I'm just given this raw data. Alright, what I'm going to do is use my data input mode to run this t-interval command. Well, our level of confidence, LOC, is my abbreviation for level of confidence, was 0.90. Let me check it. Yes, construct a 90% confidence interval estimate of the mean amount of mercury in the population of all sushi fish for all of time. Alright, so we want to construct a 90% confidence interval estimate for the population proportion of mercury levels in parts per million for all fish, all sushi fish of all time. Alright, we're going to enter this data, raw data, into list L1. That's the default. So we need to enter this raw data into list L1. Alright, and you may recall how to do that. You click Stat, hit your Stat button, choose your Edit option on the submenu, and then I'll ask us to clear the list L1 of all old data and enter in the new data. And by the new data, I mean these numbers, these 7 numbers right here. So you might want to pause, grab your calculator, and clear out the old data and put these new numbers into list L1. Please do that now. Alright, once we've completed that step, I'm going to go to the t-interval command. And again, we hit Stat, then Tests to get to that test submenu, and t-interval. Alright. In the input mode, we're going to input this raw data, so we're not going to choose the stats mode, the summary statistics mode. Be sure to highlight data and enter. Make sure that data option is selected here for this t-interval command, and you'll see the menu changes accordingly. Instead of prompting me for summary statistics, it's asking me for the location of the raw data in your calculator. Well, the default should be L1. Alright, so enter in list L1. That's where the data lies. Frequency, the default is 1. And I would just leave the frequency as 1 in the default. And the confidence level, again, we want a 90% confidence interval. Alright, once all that is entered, I'll cursor down to calculate and select, and we get the following result. Here is my confidence interval in parentheses notation, which I'm not too crazy about. I prefer this double-sided inequality notation. It's a bit more descriptive, more intuitively pleasing, I think. 0.44994 on the low end. So there is my result. From using the raw data mode on our t-interval command, I claim this is my 90% confidence interval estimate for mu, the population mean of mercury levels in all sushi fish of all time. I can add an interpretive statement here. And again, informally, I could say I can be 90% sure that my population mean is within this range. Perhaps more formally, I could say 90% of similarly constructed intervals or interval estimates will actually contain mu. Okay? Alright, so we've done one example of the t-interval command with summary statistics. We've done one example with raw data. And I guess using the raw data does save you a step or two if you've got the raw data available. Of course, it's somewhat tedious to enter the raw data in initially. Alright, I want to do number 13. Another example. We'll call it a day. Let me look at number 13 in the book. Page 357. Mean body temperature. Data set 3 in Appendix B includes a sample of 106 body temperatures. Now, there's no raw data here, so they're just giving us a summary statistics, so I'm going to go ahead and write them down. 106 body temperatures having a mean temperature of 98.2 in degrees Fahrenheit and a standard deviation, remember this is a sample standard deviation, of 0.62 degrees Fahrenheit. Construct a 95% confidence interval estimate. So my level of confidence is going to be 0.95 of the mean body temperature for the entire population. So I want upper and lower bounds for an interval estimate of the population mean body temperature for all bodies of all time. Alright. Again, we'll go to the t-interval command. Hit stat. Then tests. Then scroll down and hit t-interval because we're going to be using a t-distribution to generate this interval. Our input mode. Of course, I'm not entering in raw data, I'm entering in summary statistics, so highlight and select statistics for the input mode. Our sample mean was given to us, 98.2. Our sample standard deviation was given to us as 0.62. And of course our sample size was stated as 106. Our confidence level, how sure do we want to be to contain mu? That was 95%, or I'll just put in 0.95. Alright. Highlight and enter calculate, and I'll get the following result. (98.081, 98.319). Again, this is an interval notation, which I'm not too crazy about. I like this notation better because then I can really see you know what you're estimating here. Gives us a nice reminder of what we're really talking about in the real world here. We're actually estimating a population mean body temperature. Alright, so I claim this is my 95% confidence interval estimate for mu, where mu is the population mean body temperature for all bodies of all time. And again, I'll add an interpretive statement here. I'll say 95% of similarly constructed intervals will actually contain mu. Okay? Alright, so we'll call it a day with our new interval, our new command, the T interval command, and we'll pick it up next time. That is all for today.